Swayam Prabha. Digital India. Educated India.
Today we are going to look at some applications of the wave propagation solution that we have been discussing over the past few lectures. So, by applications I mean applications in our what we observe in daily life. So, we are going to discuss today two examples. One is that of a bar which is started with an impulsive force. So, suppose you have a bar, a finite bar So, this is our first example. We have a finite free bar which can move in this axial direction, but it is restricted in the vertical direction. So, this bar can move only in the axial direction. So, this is a uniform free bar which is given a force of strength F naught and which is an impulse, an impulsive force. We consider the axial displacement field of the bar to be represented by u x comma t, and the properties rho a and e. So, the force distribution is actually represented by, so what we have been writing, the force distribution therefore is F naught delta t. It is an impulsive force applied at x equal to 0, the way we have considered our coordinate system. So, we have this force. So, our equation of motion for this bar reads so, this is the forcing. Now, we write down the, so to obtain the initial condition on the bar, we write down the impulse momentum equation. So, this is obtained by integrating this equation of motion over time over a very small time interval. So, So, we integrate this equation over a very small time interval 0 to 0 plus. So, just after, so a time just after the impulse has been applied, and we know that this term over this very small time interval is not going to contribute to this integral. So, the terms that are going to contribute and what we obtain immediately is, so this gets integrated once and the velocity at 0 is 0. So, the velocity just after the impulse, that is what we obtain, which is represented by v naught of x. So, this is the distribution of velocity just after the impulse. So, what this means is that the velocity distribution is like this, that at x equal to 0 there is this velocity, whereas everywhere else. So, almost at all points of the bar the velocity is 0 except this this layer at x equal to 0, which has a velocity f naught by rho a. So, this gives us our initial condition on the bar. Now, when we disturb a bar like this, we give an impulse, what we expect and what we by this time whatever animations that I have shown you, you can guess that when this bar is disturbed, there is a wave front which starts propagating. This point of the bar immediately does not know that there has been an impulse. So, this whole part of the bar is stationary, whereas this layer has acquired a velocity and that information is going to propagate, and it is going to propagate at the speed c, which is square root of e over rho. So, that is the speed of propagation of axial waves. So, we have the wave field in the bar, therefore, can be written as, let me write it as f1. So, there is a positive travelling wave front in the bar. So, our displacement of the bar, the axial displacement of the bar is guided by this propagating wave front. Now, we will apply this initial condition. So, let us differentiate this first. So, that is what we have. So, f 1 prime so we have this f 1 prime. Now, we must integrate this to obtain f 1. Now, integral of this Dirac delta function is the Heaviside step function, and there is going to be a constant of integration. Now, if you use the condition that the displacement of the bar throughout, or the displacement of the bar is 0 at when even after this impulse. So, just after the impulse has been applied, the bar has taken a velocity distribution like this, but its displacement is still 0. So, which means that if you use this condition, then you can solve for this integration constant, and then this will imply that C I is which you can easily see from here, because this f1, so u x 0 is nothing but f1 of x, and that must be equal to 0. Now, this at 0 is 1. So, this becomes C1 C I, the integration constant becomes f 0 by rho a c. So, therefore, f x minus c t, which is u x comma t, becomes so, we have replaced this x by x minus c t, and that is u x comma t, and by substituting this here and finally replacing this x by x minus c t, I obtain this wave field. But this, remember that this solution is valid as long as this wave has not reached the right boundary of the bar. So, which means the validity of this solution is from 0 plus to L over c. This is the time taken, L over c is the time taken for this wave front to reach the right end of the bar. So, this is a solution that you will observe when t is less than L over c, and just after the impulse has been applied and t is less than L over c. Now, this front is going to go and hit the right boundary of the bar. So, here there is a front which is travelling, and that is going to hit the right boundary and going to reflect back. So, this is f. So, this was f1. So, this is f1, that is incident on the right boundary, and what gets reflected I will represent as g1 x plus c t. So, this takes place at t equal to or greater than equal to L over c. So, as long as this wave has not reached this is not generated, this is generated after this wave hits the right boundary. Now, then our wave field, so if t is so this is the solution when the wave goes and hits the right boundary. So, this is valid for t greater than L over C, but less than 2 L over C when this solution goes and hits the left boundary again. But so, let us restrict now to what happens just when this has reflected. Now, this boundary is a force free boundary. So, the boundary condition so, this is a force free boundary. So, this is the boundary condition. Now, when you substitute this in here, what you obtain is so that implies now let me make a substitution. Let me substitute this L plus C t, because we want to have g prime of z. So, z as L plus C t, and that means this L minus C t can be written as 2 L minus z. So, then this I can write so, g prime is given by this expression, and if you integrate this. So, if you integrate this expression, again C I is the integration constant. So, g of x plus C t now we will use the condition that at t equal to L over C, this solution is 0. So, these are all G 1. So, at because just at the time it is L over C, this is 0, this has just been generated, or just before that it is not generated. So, it is only the left. So, the wave has just reached, the initial wave has just about reached the right boundary, and then you can substitute in this, and you can very easily see that you can solve for the integration constant, and then finally the solution So, this is the solution after the wave has reflected once from the right boundary, and this solution is valid in the time interval L over C to 2 L over C. Now, once again this wave is going to come back to the left boundary. So, So, this wave is negative travelling wave, and that is going to come back to this boundary, and this is going to be a reflection. So, this is f1 plus g1, I am not writing the arguments, and what I generate is f2 x minus ct. So, this f1 was a positive travelling wave, g1 was negative travelling wave, the superposition is travelling now this, and what it generates at this boundary is f2. So, once again you consider this solution plus f2 x minus ct, and when you do these calculations, then what you obtain following the steps that we have done above. So, you will come to this expression f2 prime of z is given by this expression. So, f2 of z is and so therefore, now we use the condition that this is 0, f2 is 0 when t is just 2L over C, and that gives us once again the integration constant, which is f naught by rho A C. So, therefore, after the second reflection, now this is a solution which is valid till again you have this wave reaches again the right boundary. So, this is how you can keep solving these reflection processes. Now, if you consider this solution and plot the propagation of this wave, then you will find that the motion of the bar is something like this. So, as soon as you give the impulse, the left end of the bar undergoes so there is it acquires a velocity, and because of this velocity a displacement wave follows. So, this is the displacement of the actual displacement of the bar, it is shown in the transverse direction, but this is actual displacement of the bar, and this front propagates, and it propagates at a speed c as we have seen. Now, this portion of the bar yet does not know that there is an impulse given to the bar, the left end. So, this is in the equilibrium position, and this wave propagates, hits the right boundary, and the right boundary undergoes twice that deflection, because now it is a force free boundary. So, there is a compression wave. So, this is a compression wave actually. So, when it hits the boundary, it relaxes and it reflects back. Now, this bar here is under tension. So, this displacement front now propagates to the left again at the speed c. Again it reflects and this reflection takes place. So, what is happening in effect? So, that is very important. So, here there is a displacement after in this time region, you see the displacement stays like this, and here there is a twice this displacement. So, what we find, that displacement is continuously increasing, which means the bar is actually propagating. So, to see this, here I have plotted the motion of the ends of the bar. So, this is the left end of the bar. So, as soon as the impulse is given, so this is time, as soon as the impulse is given, the left end of the bar gets a gets a velocity, and the displacement follows. So, left end of the bar remains displaced at a constant value, as we have seen just before. Right end of the bar does not know at this time L over C, the right end of the bar knows that there is a displacement front. So, it gets displaced twice this distance and it stays here. So, this is the right end of the bar. Here the wave again reaches the left boundary, and the left boundary takes a displacement jump. So, like this the two ends of the bar, they are moving, but now they are moving in discrete steps, as you can see here. Now, this is the mean motion of the bar. So, let us see what is happening. You have displaced, you have provided this impulse to the left end, the wave propagates, and this ends get this end will undergo twice the displacement, then again the wave propagates back and pulls this. So, the bar is constantly moving like this. Now, this is a transient motion, but when we do it in a real world, suppose you hit a bar, you find that the bar is almost moving like a rigid body. If it is a frictionless surface, it will keep moving at a constant speed. Now, if you do this calculation, just little bit of calculation further over this, then you see this, the whole bar shifts a distance So, this is the distance travelled in time L over C. If you look at these plots, then you will find the distance travelled is f naught over rho a c. So, at every step you have this displacement, and the displacement takes place in this time interval. So, the average speed of the bar is f naught by rho a L. Now, A into L, area of cross section into length is the volume into density is mass. So, this becomes f naught over m. Now, that is the result that you will obtain from the. So, this m is the mass of the bar. So, this result you will obtain from particle dynamics. If you have a particle of mass m and if you give it an impulse, this is the velocity it will acquire. So, what we observe is the mean motion of the bar is what we obtain as impulsive start of a particle or a rigid body, but inside what is happening, as we now know, that it is not a steady motion with speed f naught over m, but it is a transient motion. Always there is a transient and the ends are moving in discrete steps, and that is how this bar actually moves rather than like a rigid body. So, what we see as a rigid body motion, almost a rigid body motion, is actually can be understood in terms of the wave propagation in the system, in the bar. Now, let us go to the second example. This second example is that of a once again a bar with a boundary damper. Now, here I have a bar which is connected to a viscous damper, damping coefficient is d, and this is given a force so what we are going to study is step forcing. So, this this force F is actually of magnitude f naught, and it is a unit step. So, this is the heaviside step. So, it is a unit step function. So, you give suddenly switch on a constant force at time t equal to 0. So, at time t equal to 0 you switch on a constant force like this. So, again what happens is, as soon as you switch on, a wave starts propagating in the bar. So, we have a positive travelling wave propagating in the bar, and this is going to be the situation as long as this wave does not hit the right boundary. So, this is going to be the solution as long as the wave does not hit the right boundary. Now, as soon as it hits the right boundary, we have this boundary condition let us first consider the condition at the left boundary. So, what we have is the boundary condition at this left boundary is so the force is compressive. So, for that reason we have this negative sign. So, this is going to be the boundary condition at the left boundary at x equal to 0. So, this now if you substitute this expression, this solution in here, and simplify, so this is going to be f prime. Now, let us define z as minus C t, then we obtain f 1 prime So, this is what we have, and therefore, f 1 prime x minus C t is and this solution this is the solution as long as time is less than L over C. So, using this now we can write the velocity of the bar. So, if you consider the solution form that we have, then the velocity of the bar is given by, and therefore, this becomes by substituting this expression here, so this is a positive travelling wave, and so this is of course between 0 to L over C. Now, this is going to go and so the force is now F naught. This wave is going to go and hit the right boundary where there is a damper, and it is going to there is going to be a reflection. So, if I call this as F 1, I will call this as G 1. So, the total wave field therefore, in this situation and this is so this solution, this form is valid till this wave does not hit the left boundary once again. So, till that time this is going to be the form of solution. Now, the boundary condition at the right end at x equal to L is given by this expression. Now, once you substitute this form here and use, so once you substitute this here and you do the simplifications using this expression of f prime f 1 prime, because what you are going to get here is f 1 prime, there are derivatives on both sides. So, you will get f 1 prime and you will replace that with that expression, then finally you obtain G 1 So, upon simplification you will obtain this expression of G 1 where R is this factor r is given by this ratio. So, as you can see r is always less than 1. So, this is the damping coefficient and this is the impedance of a semi infinite bar. So, this you can obtain easily. So, then once again you can write down the velocity of the bar. So, velocity of the bar is given by minus C f 1 and that turns out to be so, let me first write down now this time is from L over C to L over C. Now, for this time interval you will find that this is always 1. So, this gets simplified so this is the velocity of the bar in this time interval. Now, when this wave reaches at the left end once again, so what we have is so we have this wave propagating. I am not again writing the arguments. Now, when it reaches this left end, so this constant force is already acting, then what we have is another reflection of a right propagating wave. Now, the boundary condition at this end, so the wave field is therefore now if you use the boundary condition at the left end of the bar. So, here so what you will obtain finally when you do all these substitutions. So, at x equal to 0. So, this is the boundary condition at x equal to 0. So, this is going to be so the boundary condition at the left end was So, this was the boundary condition at the left end. So, from there we can obtain this expression, and finally, when you use the expression of f 1 in your in the here, and that will cancel off with f naught h t, because that was how we solved for f 1. So, finally, when you simplify, this is what we are going to obtain, and therefore, so we have solved for f 2 prime x minus c t. Now, so once you so since we already have this g 1 prime, so we know what is f 2 prime. So, you see we are so we have solved one reflection at the right boundary and the second reflection at the left boundary, and if you continue this process, you can keep solving one after the other, and it so happens that these reflected waves they follow a recursion. It is like this, that at the right boundary so this is at the right boundary, so the reflected wave that is generated at the right boundary is in terms of the incident wave, and the reflected wave that is generated at the left boundary so this is for the left boundary. And thus at the start f 1 prime, we have already solved this, f 1 prime is this, and g 1 prime so once we know f 1 prime and g 1 prime, we can use this recursion to find out the wave at any nth reflection. So, using this recursion relations, we can therefore write down the velocity of the bar as time progresses and it reaches steady state, because ultimately this bar under a constant force f naught is going to reach a steady state. So, let us denote this steady state velocity as v infinity, then that should be given by, so as we find velocity, it is negative c of f 1 prime plus c g 1 prime. This is what we have discussed. So, for every right propagating wave, this is going to have a coefficient minus c. So, here there will be minus. So, like this. So, when n tends to infinity, this series, if you sum up, then you will get v infinity, and if you now use the recursion relations that we have just now discussed, then this turns out to be So, this goes on. So, we have this infinite series, and if you simplify this further, and this can be summed up. We have this expression of f1 prime. So, using that we can write this as this can be cast as a geometric series and summed up. So, this when n goes to infinity, so this can this sum simplifies. And as you know that r is less than 1. So, the definition of r so since r is less than 1. So, we can make this simplification, and this therefore, so if you substitute this expression of r in here, so this turns out to be so. Now, E by rho is c square, and this c square, this cancels off. So, and a cancel off. So, this becomes f naught over d. Now, this is of course the expression of velocity. We know that if to a dash pot, if we give a force f naught and if the damping coefficient is d, then the velocity that we will have is f naught over d. So, this velocity is as expected, but then this does not happen all of a sudden. There is a transient, and this is the transient that we observe in this plot, where I have plotted the solution as it reaches the steady velocity. So, whatever we have discussed till now, I have plotted here in these two graphs for two values of r. Now, r, so I have written the definition of r here. So, r can be positive or negative depending on the value of d, let us say. So, if d is less than rho over c, then r is positive, and in that case what we observe is something like an overdamped behavior. So, the velocity, so what we are plotting is the velocity of the bar with time. So, the velocity achieves the steady state something like an overdamped system. On the other hand, if r is negative, which means d is greater than rho a c, which is the impedance of the semi infinite bar, what we find is there is an oscillation, there is oscillatory behavior before it settles down to this steady value, steady velocity f naught over d. So, what we conclude from here, so why we are calling, see when d is less than the impedance of the bar, then we obtain an overdamped kind of a response. So, what is happening is, since d is less, so the the disturbance that goes to the right boundary and hits this damper is absorbed, whereas if the damping is more than the impedance of semi infinite bar, there is a reflection, and this reflection is more than what the initial disturbance was. So, there is some oscillation before the bar settles down. So, if the damping is more, it is more towards a hard damper, then we have reflections which cause oscillations, whereas if the damping is the damping coefficient of the dash pot is lower than the impedance of the bar, then it absorbs the energy and there is no reflection. There is a reflection, but then the total response of the bar shows something like an overdamped behavior. So, in this lecture we have looked at these two examples where we have applied the wave propagation solution to understand the behavior, the transient behavior of two bars with different kind of conditions. In the first example we discussed a bar which is started with an impulse, and in the second case we have step forcing of a bar with boundary damping. Now, what we conclude therefore with these two examples is that in the steady state what we observe as almost like a rigid body motion to our naked eye, that is what we observe, that actually can be understood from the propagation of waves in the bars or in the system. So, for any system, any continuous system like this, be it a string or a bar, the steady state motion, which at least appears to be steady state motion, actually is something like a transient motion because of this waves propagating back and forth in the system. And this is what we have also observed when we looked at the animation of a string carrying a moving load. So, the motion of the string there also was something what we have observed today. It is intermittent, it is not continuous as it appears to us